is Walter Unglaub, and this is fast versus slow exothermic reaction. So when trying to characterize a fast exothermic reaction versus a slow one, a useful tool is to look at the energy diagram. So on the x-axis here, I'm going to plot the reaction pathway, which could be formulated in terms of how many products you have versus reactants in a given set of chemical constituents. On the y-axis, we will plot the potential energy of the reaction. So initially, the reactants in the chemical reaction have some potential energy, but then to initiate the actual reaction, there requires some activation energy. Now, the activation energy will be this height here. So you can think of this as some energy barrier that the reactants must cross in order to get to the products in the reaction. We can denote this activation energy as E sub A. And finally, once the reaction is complete, because this is an exothermic reaction, heat will be generated. And that heat you can think of as the difference between the potential energies before the reaction and after the reaction. So we see that the greater the heat energy, the greater the exothermic aspect or property of the reaction is. And if we want to characterize how quickly or how slowly a reaction occurs, we just have to look at the activation energy. So when the activation energy is very high, that means that the reaction requires a lot of energy to follow through. So when you have a high activation energy, you're generally going to have a slow exothermic reaction. Likewise, if this peak is relatively small, that is relative to the energy scales and temperatures in the physical system, then we're going to have a very fast exothermic reaction. This means that not much activation energy is needed in order for the heat to be produced from the chemical reaction. So this is how one would characterize the speed of an exothermic reaction in terms of the activation energy diagram. My name is Walter Unglaub, and this is fast versus slow exothermic reaction.